Hello there, great person. Welcome to this new episode of Let's React to Some Science Stuff. This time I will watch a video called The Oldest Map in the Universe, and it was recommended by Andreas Gaming 97, so thank you, mate, for that. I'm looking forward to this. So yeah, by the way, if you comment on this video and the comment doesn't show, please try to let me know, because I think there are some bugs with my comments currently. Some comments disappear. And yeah, so I will watch the video, I will pause during the video and comment on what I think, because I am a physicist and I want you to know perhaps some more stuff about what they're gonna tell me about. So if you just want someone who watched the video as a whole, then this is probably not for you. But if you're interested in some additional commentary and thoughts, yeah, perhaps you might enjoy this. And yeah, so I'm not an astrophysicist, so this is probably not something I'm a real expert in. But I mean, I've done a bachelor's and master's thesis in physics and a PhD in physics, so I hopefully will know some stuff. So yeah, but let's just get into this. Let's have some fun and yeah, see what they've got for us today. C. Yeah, it's from C. I've not.
You've probably seen or heard this thing before, right? It's static. Background noise received by a TV or radio's antenna when it is not tuned to a nearby broadcaster. Static is the result of incoming stray radio signals being picked up from different points in the sky.
Yeah.
The vast majority of these signals originate from Earth, from unwanted, leaky ground-based radio transmitters. However, a small portion of this static is actually coming from space. Not from aliens or anything like that, but from the universe itself. This static, which sounds something like what you're hearing right now, is a microwave band low-pitched humming, emanating from all regions in the sky pretty much equally.
Yeah, and I'm quite sad that these old school TVs and radios, they start to go extinct. So this is something you might not be able to tell a child in 30 years, because they don't know what you're talking about. And that's quite sad, but I mean, technology progresses. But yeah, so background radiation, inside noise, that's very interesting. I really like that. And I mean, that's an everyday application for it. So yeah. So
And if we map this noise with sensitive enough equipment, then it gives us the oldest map in the universe.
yeah,
The cosmic microwave background,
you've
aka
probably
the
seen this, yeah.
afterglow of the Big Bang. This map provides us a clear window into the early universe, and is the most deep and complete collection of cosmic knowledge that we have.
Yep.
It allows us to deduce large amounts of information about our universe today, and provides crucial evidence for the Big Bang as we understand it. That's where our story begins today, the Big Bang, all the way back near the beginning of time.
Yeah, so it's not directly the Big Bang, but when the universe cooled down enough so that microwave radiation could survive and not be involved in the processes that were before, where like pair creation and destruction. So yeah, so basically, yeah, I'm not gonna say it in detail. It's about quantum fluctuations. So it is, so to speak, the quantum fluctuations from the dawn of time, and you can see them because it's completely random. So the cosmic microwave background radiation map that you just saw is completely random, and by that I mean the if you take a little square from it, the dots will be distributed randomly. So where it's strong, where it's weak, and that's very cool. I really like that. So you can get real randomness from noise, and it's quite an easy way actually to get it. Let's go to the beginning of time, though.
The cosmic microwave background is fundamentally linked to the Big Bang. It is the relic radiation from the final stages of the early universe, before it became the vast, dark expanse that we know it as today. The Big Bang theory holds that the universe began from a microscopic volume of unimaginable heat and density little under 14 billion years ago, a volume that has been expanding ever since. In reality, the use of the word bang can be a little misleading. It suggests that a single explosion event at time zero gave rise to the universe.
Yeah, that also is something that many people struggle with. So it's not like I've actually done research on what people think about this. So most people think it's like you have space, let's say a cube, whatever, or a sphere, and in the middle there's an explosion, like from a when you watch an action movie, such an explosion. No, it's not that. It's just everything, every space itself appears, and distances between points just get bigger because space appears between them. And because in the beginning there was so few space, it was so hot. So it's like, because the space gets more, but the energy is conserved because of energy conservation. So that's why it cools down. That's what this cooling means. And yeah, so it's not like a something. So there was no space where the explosion happened in, and it's just like it's suddenly there's a lot of hot stuff in a very, very, very dense point. A Planck cell, so to speak. I think they call it Planck cell here as well. So there's a Planck cell, and it's very, very hot and very dense with energy, and it expands and it cools because of that. And because it cools, there are certain points where different things happen, like like say what I said before, the pair creation and destruction. So you might know that from vacuum fluctuations, or from energy. Let's take the energy. It's easier. So if you have a lot of energy or enough energy, that energy can turn into particles, and those particles are matter and antimatter, and they can annihilate back into the energy, and that's a process that goes around and around and around. But there will be a point in the universe where it expands so much that the energy density is not high enough anymore for that to happen. So the energy is not there anymore to create particles and pairs. So it just stays at this lower energy level. And there is a lot more like these processes. There are more of them, but this was just an example. So yeah, that's basically it. That's basically what we're talking about here.
In actual fact, it would be more reasonable to say that the universe was a giant continuous explosion up until around 380,000 years after it was born. Before that, it was considerably smaller, and its contents, all the galaxies and matter in the universe today, were crushed into an area millions of times smaller than the space they currently occupy.
But they were not there. So you did not have matter. Did not have stable matter. Stable matter could not exist in the phase, for example, that I just described with the pair creation. Because it would just turn into energy again, so no atoms could be created, so no galaxies are there. Though, and that's interesting as well, you have these quantum fluctuations, or these and they are quantum fluctuations, so to speak, because the process of energy turning into matter, it has links to quantum physics, but it has also links to Einstein. I mean, E equals mc squared is the formula you were using here. Basically, a bit more complicated, but let's say it's the formula. So that's the formula that makes this process happen. And so there are these particles are created randomly in this space that is created after Big Bang, and there are points where it's denser and less dense. More dense and less dense. So if it expands, there will be a point where there were more particles created that then stay created, and those are what probably will then someday become nebula and perhaps even galaxies that are born from that. You know what I mean? So it's like this randomness in the beginning causes every structure later on, roughly speaking. Yeah, that's absolutely good. But of course, there are no galaxies created. It's just like glowing mush of particles, and radiation.
Temperatures sat well above 100 million Kelvin, so hot that light and matter could not be separated,
Yeah, that's
locked together in an ultra-energized white-hot soup which flooded all of space.
yeah, that's because of the
As the
creation
universe expanded in
and
its early
destruction
years,
of pairs.
these contents spread out and cooled. Particles formed inside, and the white-hot soup evolved into an opaque orange fog consisting of free-roaming electrons and exposed hydrogen nuclei, known as a plasma.
Yeah.
Within
So there, I think I'm a bit rusty on that, so excuse me if I'm wrong about this. So then the phase you just described was the one I described as well. And now there's a phase they can't create and destroy themselves anymore. So there are some spots where there's a lot of matter and perhaps antimatter. I mean, we don't know why there is more matter than antimatter. Symmetry, I think that's symmetry breaking, but as I say, it's not completely my area of expertise. So we know we are living matter, not living antimatter, and there might be places where there are antimatter solar systems, not ours, but others. Or there might be that there is a little symmetry break, so there's more matter and not so much antimatter, which is strange. So yeah, and in that phase, so where there are particles, like let's say we have a spot where the antimatter somehow went away, or there is a mechanism we don't know yet, and it caused matter to stay, so matter stays, but it's so hot that it can't form atoms. It's all protons, electrons, neutrons, stuff like that. They are in one plasma, so it's not. So atoms have still not formed yet. So this is the next phase. I really like that he's going through it. It really reminds me of. I mean, I took this course 7 years ago, so I'm rusty. I'm sorry for that, but it's very great. You should know this. If you shouldn't know this, but this is something you could learn a lot about, and you learn a lot about quantum physics here if you pay attention to the beginning of this, and then you go into particle physics, plasma physics here. So there's a lot in this Big Bang model we have currently.
In this plasma, the temperature was still far too hot to allow subatomic particles to latch onto one another and form atoms, and instead they darted across space, randomly and chaotically coming together and breaking up.
Yeah, and it's like, why did atoms not get created? There is a phase, I think, where atom nuclei are not created because they as well would just be ripped apart. And then there will be a phase where the nuclei will be created, but the electrons don't stick because they're always energized. Like, you take an atom and you put energy into it, it will the electron will get out and it will be ionized, so to speak. So you have the ion left, and the ion will be what's left. So that's, so to speak, the phase before ours. And yeah, so there are two phases there, I think.
Localized interactions were occurring within the plasma as the gravitational pulling force of its matter tussled with the outward radiation pressure of its light. The colliding and dispersing of concentrations of matter generated acoustic sound waves which flowed outwards, tracing oscillatory patterns within the plasma contents, which added a degree of randomness to its near uniformity. And then, at around 379,000 years after the universe was born, it expanded to around 1/1100th of its current size.
And that's not a lot. That's not a lot. If you imagine how big the universe is today, and this is not that big a factor, that is 10 to the power of 3, that's nothing. So it's like 1,000 times smaller than now, so it's really big already. And it just came from this little Planck cell. So yeah, marvelous stuff. Oh yeah, by the way, this Planck cell is the current model. We don't know if that's true. It's likely, and from the physics we currently have, it's the most likely thing. But there might be theory, the grand unified theory of everything, so to speak, that might even make this time where the universe was just one Planck cell wide. That is something that might get changed when we get this grand unified theory, if it exists. And yeah, that's quite interesting. I really like that. It's so incredible, and it shows you that we're not at the end. And yeah, so
Interior temperature fell to around 3000 Kelvin. Suddenly, it was no longer hot enough to maintain the universe's plasma state.
yeah,
And so instead of zipping around, free-roaming electrons began latching onto exposed atomic nuclei and could remain stable. The plasma was harvested all over the universe in an event known as the Epoch of Recombination, a process which created the universe's first neutral hydrogen atoms.
yes, and sorry to pause again, but if you want to read up on this, and I think you could probably even start with Wikipedia article on this, because I think I remember it being quite good. It's nuclear synthesis, so the synthesis of nuclei, so of atomic cores, so to speak. And yeah, you can read up on that. It's quite interesting stuff. Really like that.
Unlike within an ionized plasma, photons of light are barely affected by hitting neutral hydrogen, and so light could now travel freely and indefinitely around the universe. Matter and light decoupled from each other as photons were no longer being absorbed,
Yeah,
and the universe went from resembling an opaque orange fog to a transparent black void through which light could stream.
today.
During this transition event, the final acoustic wave patterns traced into the plasma by the baryonic acoustic oscillations were forever frozen into the arrangement of the universe's contents. Atoms formed along the framework laid by the oscillatory patterns, creating denser areas where matter was in the process of coming together and sparser areas in which matter had been cleared out.
And their stars could form.
The final photons emitted by the energized plasma in its dying breaths then scattered off of this arrangement one last time, before becoming free to shoot around the universe forevermore. That's what the CMB is, the final photons of light emitted from when this plasma turned to atoms, marking the end of the Big Bang.
Yeah, and that is so beautiful. So if you, so every time you look at the picture of microwave background radiation, so to speak, you see exactly the distance the light would have traveled from this phase, this moment. So in a million years, you will see things farther away, so to speak, because it took longer, and you see the background. So, and perhaps 1 million years after this happened, if there would have been a planet Earth where we would have lived, and you would look up, the background you saw was 1 billion light years. 1 billion light years away, yeah. So, and now it's 14 billion light years away. It just hits us, and it's expanding, so to speak, as well. And it's very cool. So it's so far back into the past is this that I can't even fathom it. So great. And the video, by the way, is marvelous. Marvelous.
Therefore, the CMB is the oldest light in the universe that we are able to see or detect. But these aren't photons of visible light anymore. The universe has been expanding for almost 14 billion years ever since, and all the while its growth has been stretching out waves of travelling light in space, reducing their photon energy and shifting them through the electromagnetic spectrum. Today, the CMB's photon energy has been reduced by an average factor of 1090.
Yeah, and that's because of the universe growth, because that's what I said, the space is like stretched by expansion. It's not like things move farther apart, but space itself is stretched. So a very high energetic wave will now be distributed across a longer cross section, so to speak, and that's why it always the same energy will always be, so to speak, dragged across farther apart points. So the energy gets lower, and that's why from like high energy photons or electromagnetic waves, there will be these microwave photons now created. Because microwave is also photons. I hope you know that, and I'm not surprised, because if you didn't know, it is. Microwaves are also photons. So
Before long, these photons were redshifted out of the optical spectrum and into the infrared spectrum, and then into the microwave spectrum, where we can now detect them as this faint humming between the airwaves. Thus, if we map this ancient cold light precisely enough, we can analyse the universe as it was during the moment of recombination, only 379,000 years after the birth of the universe, the furthest back in time it is possible to look.
Yeah. This
is why the CMB is commonly referred to as the afterglow of the Big Bang. It is relic radiation from the final seconds of the universe's fiery initiation, and it yields an incredible wealth of information about the properties of our universe both then and now. There are still many unknowns, and we are always striving for greater accuracy, but if nothing else, the CMB's existence effectively proves two things. The first is that the universe is around 13.8 billion years old, and the second is that it was much smaller and hotter early in its life. Two major postulations of the lambda cold dark matter model of cosmology, the standard model for astronomers and the theory you're most likely to find in the textbooks.
So cool. What a great
This
video.
afterglow has been present in the sky for as long as humanity has existed. But we didn't discover it until the 1960s, when the advent of radio astronomy first allowed us to pick it up. On the 20th of May 1964, American astronomers Robert Wilson and Arno Penzias of Bell Telephone Laboratories were attempting to use the Holmdel-Horn antenna in New Jersey to search for sources of static, so that they could improve the quality of telecommunications. What they found was that, no matter where they tuned their antenna, there was always a consistent excess temperature which could not be accounted for. In the words of Penzias himself, it wasn't until they had exhausted every other possible explanation for the sound's origin that they realised they had stumbled across something big. And something big indeed it was, arguably one of the most important and iconic scientific discoveries of all time. Initially, radio technology wasn't sensitive enough to detect any variations in this microwave humming. This is because the CMB has a nearly uniform average temperature of 2.725 Kelvin.
I'm sorry to interrupt this. I'm just thinking so much about this, and I'm not sure. I might misremember the story, and I thought it was their story, but he said they were Americans and used this telescope. But perhaps I'm misremembering the story. But someone once told me in a lecture where there were several scientists, and we got a talk from this guy who knew a lot about astronomy, and he told us, and I think it was this discovery, so I'm a bit confused here, but it might have been, it was in this area, it was something with microwave background. I don't know if it was its discovery, but it has something to do with it, so I will just tell it now because it's very nice and quite a funny story, and also a sad story if you really think about it. So was discovered by these two people, and one of them I think was Dutch, and yeah, I think it was something, it was Dutch, yeah, exactly, in 1962. So they were or Polish or whatever, I don't get it together. It was a man who was in a country here around Europe where they were not allowed to publish science freely. So they published this or something that is linked to this. It's probably something linked to this, but they published it in a garden magazine because they couldn't get it into a journal because the journals were prohibited by the government. And to this day, this garden journal is cited everywhere to honor the garden journal that published these scientific results. And I don't know if it is this result or if it is something closely linked to it, but it has to do with it. Just the anecdote I wanted to share quickly because I thought that was so cool. So this garden magazine, it had nothing to do with this, and they just published it there because they couldn't publish it anywhere else, and everyone honors it. I love this story. Yeah, actually, let me. I won't find it. I would have looked it up, but you can look it up perhaps. If you find it, let me know. I think it is this discovery, or it is the discovery perhaps of I think it's this discovery. I'm pretty sure. So, yeah.
with variations of only 1 part per 100,000 or less. And so, when we started surveying the microwave sky, it seemed to be completely uniform. But we've spent over 60 years and more than $1 billion refining and improving our mapping technology, revealing tiny temperature fluctuations on scales of a matter of microkelvin, known as anisotropies. The CMB's anisotropies are its tiny treasure chests, containing some of the most important information about the universe ever discovered.
Yeah, and for everyone who is not used to measure temperatures, these microkelvin, that is so hard to measure. I'm sure there's equipment they use where it's easier, but if you like take an experiment you do in school where you measure the temperature, the thermometer you use is exact to perhaps half a Kelvin, perhaps a bit more sensitive, but that's about it. And it's one of the because yeah, I teach teachers. So that's one of the thing they have most problems, because if you do experiments in school in front of students, they tend to go wrong because thermometers don't work properly and they are icky, you know? And this microkelvin, it's such an achievement to do that, to really measure temperature to this degree. That's absolutely fascinating, and what a marvelous thing.
The first and largest anisotropy we found was a temperature change of around 0.008 Kelvin. On this scale, the microwave sky appears to resemble a yin-yang symbol. However, this is not a result of the Big Bang, but rather a result of the Sun and the Milky Way galaxy moving through space towards a series of galaxy clusters known as the Great Attractor. This creates a temperature gradient in the microwave sky from one side to the other, known as the dipole anisotropy.
Interesting, I didn't know that.
Once we'd smoothed that out and accounted for the dipole, we had to get down to scales of around 30 times more precise before we were able to see any real differences. NASA's first big breakthrough contribution to this quest was the Cosmic Background Explorer, also known as COBE. It launched in 1989 and collected data up until 1996. It built upon work from previous ground and balloon-based experiments to study the CMB, and gave us our first full-sky map of the microwave background. It is said that COBE was the start of cosmology as a precision science.
Yeah.
It wasn't nearly as sensitive or accurate as the equipment we have surveyed the CMB with since, but it nonetheless mapped large-scale anisotropies, and gave us our first complete view of the whole universe at once.
Yeah, and that's because you don't have the atmosphere between you and the things you want to measure. Measuring that through the atmosphere, I don't think that's possible. You have to go into space, so like Hubble or stuff like that.
In the early 2000s, NASA launched the Wilkinson Microwave Anisotropy Probe, also known as WMAP. It launched in late June 2001 and ran up until 2010, surveying the background radiation from more than 1.5 million kilometers away from the Earth. It gave us considerably more accurate and detailed measurements of the anisotropies, and revealed heaps of new information about the age, size, and structure of the universe. It revealed that the universe was about 13.7 billion years old, but that stars may have begun forming as early as 200 million years after the Big Bang, far earlier than anyone had predicted. And then, while the WMAP satellite was still active in 2009, the European Space Agency launched the Planck Satellite, by far the most sensitive and sophisticated mission to date. It was deactivated only 4 years after its launch, but this $700 million spacecraft nonetheless gave us our most precise, deep, and complete look at the afterglow of the Big Bang.
Confused it with Hubble. I'm sorry.
It remains
Stump.
our
Hubble
most
is not.
comprehensive snapshot of the early universe to date.
Yeah, this is the one that was in the media, I think, as well. Picture you just saw.
The Planck Satellite gave us our most accurate measurements of the universe's age, its ratios of baryonic and dark matter, and its rate of expansion. It recorded anisotropies on a scale 3 times more sensitive than WMAP, and surveyed 9 frequency bands in comparison to WMAP's 5, enabling a much clearer and more concise view of the universe's anisotropies. So what exactly do these anisotropies tell us? Well, there are 2 main types of fluctuation: primary anisotropies, which are a direct result of the baryonic acoustic oscillation patterns frozen into the universe's plasma when it turned to atoms, and secondary anisotropies, which are a result of stuff in the way of the CMB photons as they have travelled towards Earth, like galaxies and voids. Therefore, this provides a great way for us to get a sense of the universe's large-scale contents. Where we see red, warmer areas, we are looking at galaxies and galaxy clusters, whereas the cooler blue areas correlate to voids and supervoids. The colours on the map do not represent absolute temperatures, rather they show the level of deviation from the CMB's average temperature of 2.725 Kelvin. But
Oh wow, yeah. This is, by the way, I would mark that if someone gave me this in a in a lab report. I would mark this, and because normally you put the same amount of digits after the point in both sides, so there are, even if it's 0, so there are 2 zeros missing, just because I want to tell you how much of a party pooper I can be. But yeah, I mean, look at that. That's absolutely this uncertainty. Wow, to get this with temperature, that is beyond. Wow, how are they doing that? I have to read up on that actually. I'm quite interested in this because that is so hard, so incredibly hard, such a precise measurement. Wow.
as we mentioned, these deviations are on tiny scales of a few microkelvin, extremely marginal when compared with its absolute temperature. In a broad sense, the CMB shows us that the universe is smooth, isotropic, and randomly distributed across its entire expanse. There are variations in gaps in space which are significant when compared with us, but when viewed on a wide enough scale, such as the CMB, these variations iron out to show a strikingly smooth cosmos, with its contents spread in a manner analogous to a homogeneous hot gas. This informs and affirms one of our most fundamental yet controversial assumptions about the very early universe: the idea of cosmic inflation. In order for the universe to be so well distributed even to this day, it must have been scaled up in size incredibly quickly and radically from its primordial state.
Yeah, and by the way, I don't know if you know this, this inflation, it can refer to 2 things. It can refer to the Planck cell expanding into what we have now, or there was a point where the acceleration of the expansion was like a jump, and that jump is really strange, and we don't really. Is there an explanation yet? I'm not sure. There might be an explanation yet, because I'm not into this field so deeply. But yeah, so there is this one area where it was some explosive expansion, so to speak. It just suddenly boop, went up. Yeah, that can also mean inflation. So that's what some scientists mean when they talk about inflation. So I don't know what he's referring to here, but I think reading this sentence, I should just keep watching and he will tell me.
The inflationary theory states that one of the earliest things to happen after the universe was born was an expansion event which appears to have violated all known speeds and laws in the universe today.
Yeah.
Space was scaled up from nanometers to light years, all in less than a microsecond. When this happened, the tiny irregularities and deviations in the very early universe's ultra-compressed contents were smoothed out. The only fluctuations that remained were caused by small quantum ripples in the inflation energy field, which gave rise to the minor variations that we see today.
Yeah, that's the one I talked about. These quantum. That's why there is quantum randomness in the microwave background. It's not because the randomness was, and it's also quantum physics and randomness a bit. But when the plasma cooled, so that we got atoms, that part where they rightly said that that was what it caused it. But before that, that was caused by these quantum fluctuations. Yeah. Yeah, it has skeptics though. The people I know, and they're quantum physicists, most of them believe in this. Or yeah, believe is a word perhaps a bit misleading there. Most of them say this is a feasible thing to assume. Let's put it that way. I think that's the best you can say about it.
This theory has its fair share of skeptics, to be sure, and perhaps with good reason. But the remarkable uniformity of the CMB shows us that inflation fits the facts as well as any other alternative explanation.
Actually, to be really transparent with you, I would like to hear those arguments, because that's how you can get into perhaps new fields and you get new ideas and stuff like this. So I would have been very interested in the counter arguments here, because I don't know them and I would like to know them, because you always need to know the counter arguments to your assumptions, because otherwise you will not learn. So yeah. By the way, something for everyday life as well. Yeah, works remarkably well.
If the
If you let it
universe had
happen.
grown any slower or in any other way, then gravity would have had more than enough time to distort the uniform structure of matter. No other theory can explain the CMB's origins and properties so precisely, and thus its existence lends a lot of credence to the Big Bang theory, cosmic inflation, and the lambda cold dark matter model overall.
And that is also something, I don't remember if I talked about this before, but this is the core of physics. So many people wrongfully assume that you discover something and that's the new law, and then that's how it is. No, it's not. Physics is not rigid. Physics is evolving. We don't know anything, so to speak. We only have models. Everything in physics is a model. And you model things, and if there are things your model can't explain, you adapt the model or you create a new model. And it's actually exactly the same what happens in your brain when you learn something new. But it's also how science works. So he put it exactly correctly. It works. It's the best working theory, so we take it. So the Big Bang theory, although it's just gathered from data points and its assumptions, so to speak, it is the best fitting explanation to all the data we have. And there are problems with it, I think. And with every model, there are problems always. So we are searching for ways to iron out those problems by either expanding upon the theory or taking a new one that explains it better. And that's how physics works, how physics grows steadily. So if someone says, yeah, but we know that, no, you don't know that, you know the best working explanation for it. We know. It's a slight difference, but without this difference, physics would not work. And yeah, just something that's quite important to me, because this is something where I often hear that said that, yeah, but science tells you that. No, science tells you that this is the best explanation. It's not the only and not the true explanation. It's the best working one. That's all science can do. It can do nothing more. But that's still very much it can do. So yeah.
So that's the story of the cosmic microwave background and of our universe. And, like with any great discovery in cosmology, there exist anomalies and unanswered questions within the CMB which
that's what I'm telling you.
For.
That's exactly
Specifically, anomalously warm and cold areas of the radiation which seem unnatural when compared with the near uniformity of the microwave sky. Let's start with the latter, an unusually large and cold anisotropy in the southern galactic hemisphere, aptly known as the cold spot.
Great name.
The cold spot is an area of the CMB where the temperature drops very sharply when compared with other anisotropies.
Yeah, just some fun stuff. I'm not sure about this, but I know some colleagues who do this. They give stupid or cool, nerdy names to things. And most of the things we know are, yeah, it's just like a pet name they choose, and then it develops into the real name, so to speak. And this cold spot is probably like they were in their office, and it wasn't the ones that, oh, that's quite a cold spot. Yeah, let's call it the cold spot. Why not? Let's have some fun. I bet that's how it came to be like that. It's not like they are thinking, and yeah, what are we gonna call it? No, it was just probably some dude perps with a beer after having finished work for the day, taking a beer from the fridge. I mean, I'm German, I say beer, perhaps a whiskey, wherever you are, I don't know. I said, yeah, look at it, it's quite a cold spot, isn't it? I bet that's how it was created, knowing scientists. Perhaps they drank apple juice. And I don't want to imply that they drink alcohol, but they probably were relaxing after work and they looked at it, or during a break, and they said, yeah, it's quite a cold spot there, let's call it cold spot. I can totally imagine that, because that's how I think some of the physicists then would definitely be like that. Some others wouldn't be, but I think half of the names probably are created like that.
Implying that there is something more at work than simply a less dense region of space.
Like quarks. That name's, yeah, whatever. Or like Thomson called electrons corpuscle in the beginning. Yeah.
This anomaly was first noted by the WMAP satellite, before being unexpectedly detected again by the Planck Satellite, effectively ruling out the possibility of it being a data processing error. Whatever the cold spot is, this thing actually exists somewhere out there in the darkness.
Pretty creepy.
The anomaly is located predominantly within the constellation of Eridanus, and has a width in the night sky of more than 20 times the diameter of the Earth's moon, correlating to a cold, empty patch of space hundreds of millions, or perhaps even billions of light years wide, making it one of the largest things in the known universe.
But could you not calculate the size quite precisely? Because you know how far away it is, because you know how... Or perhaps you don't. But I mean, we quite precisely know when it was, I think. So you might take that and take the distance, and then you can just calculate the arc length of that little bit. I don't know.
It is several times larger than the average size of cold anisotropies, and while average temperature fluctuations within the CMB are around 18 microkelvin, the cold spot dips by an average of 70 microkelvin. And in some places, it drops by more than 140 microkelvin. Voids and supervoids can usually explain such large cold areas, because voids have a diminishing effect on the energy of the photons travelling through them, including the CMB photons. But even the light-sapping effect of a void of this enormous unlikely size would not be sufficient to account for the sharp drop in temperature that we're seeing. In fact, some scientists argue that Big Bang cosmology and the idea of a smooth isotropic cosmos cannot account for such a large anomaly, period. If the universe really is nearly homogeneous by the grace of cosmic inflation, then such a universe should not be able to naturally give rise to such a large, empty and cold supervoid.
But we might overthink this, because it is quite often so that there is just randomness. It might be randomly that cold, and you see a pattern there because you're a human, and I've talked about this a lot already. So you see patterns, pattern recognition, like you see faces in a soup or whatever, and it's your brain is wired to do that, and your brain is wired to detect anomalies, basic survival instinct from way back when, I don't know, we were on trees and, I don't know, we're apes, whatever, and that might be this. Might be just coincidence.
And so naturally, the inexplicable nature of the cold spot has led to wilder, more eyebrow-raising theories.
Yeah, let's see what they have.
Perhaps among the most interesting of them is that the cold spot is what's known as a cosmic texture, a damaged or defective area of the universe, analogous to a crack within an ice sheet. No known physical mechanism could allow for such a defect in space, and thus cosmic textures are hypothetical at best. But some have taken this a step further, claiming that the source is extra universal.
Might be, but
some propose
what a
that the
reach.
cold spot is a bruise from where our universe bumped into another bubble universe.
Yeah. That might be. Though it's a lot to explain what might be randomness. I don't know the data on this, of course. I don't know how random it is and how unlikely it is to happen, but yeah. So we are pretty sure that parallel universe like this exists, so not a universe where I am like not wearing this bow tie but a normal tie and everything else is the same, you know, this science fiction parallel universe. No, it's just like another universe where perhaps the laws of physics are a bit different. Like I talked about this in the black hole video where I talked to you about the theory that universes are procreating by using black holes to create new universes like that. So perhaps a neighboring universe. Though this bubble thing is again too much, too literal. I think you have to be careful with this, not taking this too literal as well, because it's just a metaphor. Like there are not two balls that bump into each other. That's 3-dimensional and universe is at least 4-dimensional. So, but it's a neat analogy.
While others propose that the cold spot is an imprint from where our universe became quantumly entangled with a perfect parallel when it sprung into existence, before the two were separated by cosmic inflation. But those are admittedly some pretty outlandish and at the moment unevidenced hypotheses. While it is an intriguing mystery and a spooky coincidence, the cold spot is more than likely going to be due to some kind of improbably large void, perhaps with the help of a few data processing artifacts or something in the way to enhance the effect.
Yeah, that's what I'm
Occam's
thinking.
razor and all that.
Yep.
But don't get too disappointed, because the cold spot is not the only anomaly on the CMB which might imply some kind of alternate reality. And in contrast to the cold spot, these anomalies constitute
not alternate reality, alternate universe, it's different.
Significantly warmer than average regions as opposed to cold ones. I'm talking about Hawking points. Powerful spherical sources of energy within the CMB, around 8 times the diameter of the full moon. Within these spots,
and what he's saying by this diameter of the moon thing is like when you look at the moon and it's next to the moon, that's
the temperature fluctuates sharply upwards by more than 30 times the mean temperature increase for warm
might be a giant black hole,
suggesting that they are sources of high amounts of photon energy. These points went undetected for the longest time. It was assumed that any anomaly like this would be an artifact of data processing, as cosmic inflation wouldn't allow for such irregularities. But after being noticed on the Planck Satellite data, these points were then confirmed within the WMAP data as well. Analysis has since revealed no less than 30 of these points within the CMB, and some scientists, in particular Oxford mathematician Roger Penrose, believe that these points are in fact echoes from a previous iteration of our universe.
But it might be a giant black hole.
To understand why, one must consider an alternative twist on the Big Bang Theory, namely the paradigm of conformal cyclic cosmology, which proposes that our universe is just one in a number of so-called aeons, or cycles, of our universe being born, expanding, and then collapsing down into a new Big Bang to be born again, with the process repeating at infinitum.
Why would it? And this is not a doubtful question, just a question to you to think about. Why would it come together? We would need a new law, I think, that would describe that and would incorporate that. So, I don't know. It's a nice idea, though, and it might be possible, but you would have to put more things into your model. And I don't think we can model that. So we also have no idea when it will happen, if it would happen.
Not a parallel universe, like what's being suggested with the cold spot, but rather an oscillatory universe, which expands up and then squashes down repeatedly. One of the major selling points of conformal cyclic cosmology is that it offers a slightly more explainable hypothesis for cosmic inflation, moving it to before the Big Bang of our universe. The theory suggests that what we perceive as cosmic inflation in the nanoseconds after the Big Bang was actually the very remote far future of the previous universe, which was so old and vast and expanding so rapidly that it mimicked the behaviour of what we believe happened during the inflationary epoch of our universe. So where does the CMB come into all of this?
Yeah, and if it's expanding, how is it shrinking? What? I don't understand that. I would have to read up on this.
Well, conformal cyclic cosmology proposes that during the previous universe's rescaling event, when it is squashed back into a new Big Bang, the only thing that will exist by then are black holes, which will have had more than enough time in their remote futures to consume their entire galaxy groups and each other, leading to a few unfathomably massive black holes dotted around the enormous universe. But this exponential expansion in the previous universe's future occurs at near time-like infinity, long after even the largest black holes will have evaporated into Hawking radiation. The Hawking radiation is what will then be squashed back into the new Big Bang, but rather than being blended in with the new universe's contents, this energy is retained as a single point which persists into the new iteration.
Okay, I understand that, but why are there then only 30?
It is only during the new universe's Epoch of Recombination, when its CMB is created, that this photon energy is freed. And if all this is true, then by now, any such point in the preceding universe should be about 3 or 4 degrees of the sky across, around 8 times the diameter of the full moon. And sure enough, this is what has been seen in the CMB data, and proposed by Penrose et al. As evidence of an oscillatory universe.
Okay. That actually, I did not know that, and that sounds incredibly plausible, though, as I said, we still don't have the mechanism. Why would that happen?
Pretty spooky, right? There are no less than 30 of these points lurking within the CMB map. The question is, are they really the evaporated ghosts of 30 massive monster black holes from a previous universe? Not everybody thinks so. Follow-up studies have suggested that the findings for Hawking points are not as statistically significant as they were first thought to be. In summary...
Wait, good, here's the paper. Very nice, very nice. I like that he does that. Yeah. Let me go back a bit. I'm sorry.
As they were,
and I will put out the... Okay, yeah, this is statistically absolutely worthless. If this is true, it's just random noise.
First thought to be.
I said, I don't know if you know about these sigma. So in physics, and this is also like you cannot never be sure. So if something is 5 sigma, that means in the 0.0000001% of the statistics to create this, the zero hypothesis. So like the zero hypothesis is so nothing is there, and you propose there is something. So you say, yeah, I propose there is something, and I will only say there is nothing. No, and I will say there is nothing if I measure certain things, and the probability of measuring these things is expressed by this in a way, not directly, but so the bigger this sigma, so 1 sigma 2 3 4 5, the bigger this is, the less likely it is that there is nothing, that you have actually measured something is higher and higher the probability. So, okay, so I hope this was just stupidly explained. I could do it better if I thought about it more. I'm sorry. So yeah, that's like also the Higgs particle, like when it was discovered, they were all waiting for the confirmation of 5 sigma, and this neutrino or neutron or whatever things that they might have discovered last year, I think, they did not reach 5 sigma. So they are just statistics now. if something is 5 sigma or more in physics, it's convention. So we agreed on this as a community. I mean, I did not, but people before me, they agreed on this. They agreed on if something is 5 sigma or more, we say it's there. Only then. So this is not more than 1. So it's basically randomness. It's just coincidence. Interesting. I'm very glad that, and he seems to know his stuff because he showed exactly the right point in the paper I needed to see. That's very, very good work. Very good work, actually. So I can instantly evaluate this.
In summary, the jury is still out on the nature of Hawking points.
I would not say that. I would not say that. It's a nice theory, but if it's 1 sigma and the calculations are correct, I mean, I haven't checked them, but if the calculations are correct and it's 1 sigma, it is not, we would say as a community, it's random. Though it's, again, it's what we agree upon that's the way we interpret it. They agreed upon where we interpret it. So it might still be true, but it's so unlikely that the community says, if it's by the standards of our community, in the physics community, we would say, no, it's not the way. But again, then there are people that say, yeah, but it could be. And that's valid as well. That is also a valid point. It's just not the thing, like the way we would do it normally. So you would have to give good reasons why you get away with this and why you would do this. Like in a particle accelerator, how many collisions are there? So many collisions. And if you have a trillion billion collisions and you have the data from all of them, there will be outliers statistically. Even if it's just 0.0001%, if you have a trillion measurements, it will happen about 100 times or more. So yeah, that's why we have to agree upon something, and that's 5 sigma, and this is not 5 sigma. So from my point of view, it's nothing, but I might be wrong on this. We can't know this from this data, but it's so unlikely that from the things we do as physicists, the way we work, let's say it this way, the way we work, we would say this is nothing. And I agree, because I would say I need more evidence. That's what I would say. I would need more evidence to believe this thesis of Penrose, because this is not evidence for me. This is just randomness.
As it is for the nature of the cold spot. These two classes of anomaly on the CMB may not indicate new universes, and may instead be illusions caused by data processing artifacts or chance alignments.
I'm not so sure why he says might, because I'm sure he knows this. He put the right thing from the paper. He should now say, so from our perspective, it's nothing. And it might be this, just an artifact. Like, he still talks as if the theory is the one accepted, but if this is the real result, and hopefully there are other studies that confirm this 1 sigma, but if that's what it is, he has to say, no, it's not what we think is actually happening, because it's too unlikely. That would be the reason. It's too unlikely that this is true. Not impossible, but too unlikely.
Even if the CMB doesn't contain any information about other universes, it still contains almost an unknowable amount of information about ours.
Yeah.
From its earliest years, to its present day contents, to where it's headed. The CMB has been cooling down ever since it was first created, and it will continue to cool until it eventually becomes so faint that it is superseded by the radiation from other stars, and it will never be detectable again.
So sad.
But if what we've discussed about cyclic cosmology is anything to go by, then that will by no means be the end.
But why would you say this? You just showed me a paper where it says it's so unlikely that we would normally say no. It's so unlikely we don't think it's a reasonable interpretation currently. I don't know. Great video. Very, very, very good video. Absolutely stunning and marvelous. Stunning, brave, marvelous video. couldn't resist. Yeah, I really like this, so I will watch more of theirs. They did a good job. They scratched the surface, and I'm really glad they did nothing save for the end bit, which is really finicky and really party poopery by me saying that, so doesn't really matter. This was a marvelous video. You should watch this. It tells you a lot, and if there are things in this video you are interested in, you can look them up. Wikipedia is actually quite a good source for this, so, or you might look into a textbook on cosmology. I think most of them have this. Nuclear synthesis, or you Google it, there are a lot of explanations. And it's actually not that hard. If you know a bit about atoms, like your school knowledge should be enough. If you have passed through school and understood all of physics, at least that has to do with particles, like atoms, if you understand everything with atoms and what structure they have theoretically in our models, then you can understand the nuclear synthesis. And you should read up on this. So, I like this video. Andreas Gaming 97. Thank you again for recommending this to me. This was really great, really great. And yeah, I hope I didn't talk too much again, but yeah, I'm a bit sad that I did not remember the correct story from the gardening journal. So you might look that up. It's quite fun, but I think it were those two. I think it were those two that published it in the gardening journal. Such a great story. But also sad because, yeah, I mean, of course it's sad because they couldn't publish it in a journal because science was prohibited in certain ways. So, always bad. Science and education should be free. Should be free. So, anyway, if you like this stuff, consider liking, subscribing. I will do more next week. I also do my Doctor Who reactions currently, and I will start Wheel of Time when it starts coming out. And Foundation is almost over, so you might watch that as well. I've got a new setup for reactions. I mean, if you check out my Doctor Who videos, you will see my new setup. And again, if I don't answer to comments, please check if they're still there. They might be gone. I'm sorry if that's the case. I did not change anything in my settings, but you know. Anyway, I hope you have a wonderful day and hope to see you soon around, and take care of yourself. Bye.